Students, hi, this is Mr. Bob, and in this video, I'm going to walk through a sample angled projectiles problem, and I'm going to walk through and just kind of show you the different ways of solving different aspects that you can typically see in a problem like this. I do emphasize that, or want to emphasize that as much as possible, I would urge you to pause this video at each part and see if you can work out the problem on your own, and then obviously continue watching it and see my method. Also, I want to emphasize there's more than one way to solve some of these parts to this problem. So if you solved it a different way, it doesn't necessarily mean your way is incorrect, uh, as long as you got the same final answer that I did. Okay, so here is the sample problem. A child is playing with their stomp rocket toy. They launch a rocket at an angle of 53 degrees above the horizon with an initial speed of 24.0 meters per second. And it says assume the air resistance is negligible for this entire problem. And there's four things that need to be determined. A, the initial horizontal and vertical velocity of the rocket. B, the time for the rocket to reach its maximum height. C, the maximum vertical height the rocket reaches. And D, the range. And the range is simply the horizontal displacement from the launch spot to the landing spot. So as usual, I am going to follow what I've been talking about since the beginning of the year, the DGuess method. And I think this is especially important here to help you keep things straight in your head and to minimize the chances of making mistakes. So the first part of that is the drawing. So making that drawing is really key. And so part of that drawing is actually just, making a little drawing of a rocket. I'm going to try and just do this really quickly here. Okay. And so the coordinate system is really key here. I'm going to make the rocket departing at the coordinate system. I'm going to assume the coordinate system is basically centered there, so to speak. And this is the Earth, the surface of the Earth that we're on. Okay. And within that coordinate system, you can see that the problem tells me that this is a 53-degree angle. Okay. And so what I know is happening is this has some sort of initial velocity here. In fact, I'm told the initial velocity is 24.0 meters per second. So let's actually start filling out the data table here. And notice I have the table that we've been talking about with the two columns, the two rows for the horizontal values and the vertical values. And we have to remember what we've talked about in class, which is this can be broken down because air resistance is negligible. There's a symmetry to this problem. And we can look at the two motions, the motion in the horizontal direction being independent and doing something slightly differently than the motion in the vertical direction. Horizontally, what do we know? We know that after the rocket is launched, basically that object continues to move at a constant horizontal velocity. So whatever speed we figure out the rocket started with horizontally, that's going to be the same throughout. So in other words, these two values are going to be the same. Vertically, we know it's accelerating, and because we assume air resistance is negligible, it is into free fall. So right away, what do we know? We know that the acceleration has a magnitude given down here as 9.80 meters per second squared. And let's just be very explicit here in our coordinate system, just to make sure we know that we're going to assume that down is negative, up is positive, and to the right is positive. And we're going to assume the rocket's moving to the right. So with that in mind, we know the vertical acceleration is negative 9.80 meters per second squared. And I already said that the horizontal acceleration after launch is 0. Okay. We also can tell from our coordinate system that the initial position, vertical and horizontal, is 0. And that's all we can tell for now from the problem statement. Okay. So now let's go ahead and start solving the problem. Let's start with part A. I'm going to choose blue as my color. So part A, we want to figure out the initial horizontal and vertical velocity of the rocket. And to do that, we need to recall our trigonometric functions, okay? Because what we have here, I'm writing down SOHCAHTOA, and I'm also going to draw a little triangle here. What we have here is we have an initial velocity. But remember, we can recast that as being basically the sum of two vectors, initial velocity in the x direction and initial velocity in the y direction. And this is still our 53-degree angle. And when we do that, notice we have a right triangle here. Okay, then we can use our trig functions because what we're trying to find is the length of these sides. Okay, and let's start with the horizontal. So let's go back to blue. Horizontal. So horizontal means VIX, and so that is the side that is adjacent or next to the angle of 53. So we have adjacent, okay, and we also know the length of the hypotenuse. So adjacent hypotenuse, that means we're going to want to use cosine to figure out that horizontal side. So cosine of 53 degrees equals the adjacent side, which is VIX, over the hypotenuse, which is VI. Now, when let's solve for VIX, that's what we want to do. If we multiply both sides by the initial velocity, then this is going to cancel. And what we're going to get is that the initial velocity times the cosine of 53 degrees will give us the initial velocity in the x direction. So if I put in 24.0 meters per second times cosine of 53 degrees, if you punch that in your calculator, you get a value of about 14.4 meters per second. Okay, so I'm going to go back up and I'm going to put that in for my initial velocity. And I also know that that's my final velocity too. So that's my horizontal velocity for the entire problem, 14.4. Okay, now let's do a similar thing, but for the vertical direction. So that was horizontal. Now vertically, what do we have? Let's see, vertical, this is opposite the angle. So opposite, and we also know the hypotenuse. Opposite hypotenuse looks like sine is going to be the one we have to use here. Sine of 53 degrees equals VIY over VI. And similar to what we did last time, if we multiply both sides by VI, then we will basically get an expression that allows us to solve for the initial vertical velocity. Plug in the number for the initial velocity, punch some numbers in our calculator. We get that the initial velocity in the vertical direction is 19.2 meters per second. Going back up here, we can now fill in this one. So we have solved part A of the problem. Awesome. Again, reminder before each step, if you can, please try and solve as much of it as you can on your own and then check your answer. So pausing the video is a good idea. So part B, the time for the rocket to reach its maximum height. Let's go down here and figure out part B. Part B, let's see, we have to look at these equations now and we have to figure out which of these helps us figure out this given the information we already know. So we're looking for time, and notice if it's time to reach max height, height is a vertical thing. So we have to look at our vertical values. They're the ones that are going to help us here. So notice we know the initial position, we know the initial velocity, we know the acceleration. Then one other piece of information that we have to remember is that in the vertical direction, what happens at the max height? What do we know is true at that split second at the max height? Well, we know that at max height, the final velocity is what? 0 in the vertical direction, okay? This is really key. At max height, the final velocity in the vertical direction is 0. So now we have initial velocity, look, we have final velocity, and we know the acceleration. So notice this equation right here is the most easiest one for us to use because we can get the time from it, which is what the problem's asking for. So we're going to say that the final velocity in the vertical direction equals the initial velocity in the vertical direction plus the acceleration in the vertical direction times time. I'm going to solve this equation for t. So I'll subtract VIY from both sides. I'm also going to then divide both sides by the acceleration, and I will get an expression where the time is equal to the final velocity vertically minus the initial velocity vertically divided by the acceleration in the vertical direction. Plug in my values. We said the final velocity vertically was 0. The initial velocity vertically, 19.2 meters per second. I want to urge you, one thing I see students do very often is they confuse. They might put, say, 14.4 meters per second in here incorrectly. So always a good idea to double check that and to think through that before you just grab a number. And the time, the acceleration is negative 9.8 meters per second squared. And it's negative 9.80 actually, to be exact. So divide that in your calculator and you should get that the time is equal to 1.96 seconds. And I'm going to start just making these answers stand out by putting little boxes around them. Okay, so just under 2 seconds. So we can go back up here. We can say this is 1.96 seconds. I do want to emphasize this is max height because you'll see in a second here why. So that's the max height time. Okay, part C, the maximum vertical height the rocket reaches. So we're looking for vertical height now. Okay, again, this becomes an exercise in thinking through, okay, what information do I have in my table now? And compare that to these equations here. Now, there's a number of ways you could do this. I'm going to home in on this equation when possible. I like this equation. I think it's easy to kind of manipulate mathematically and less prone for a student to make errors. So notice, do I know the initial velocity vertically? Yes, I do. Do I know the final velocity vertically at the max height? Yes, I do. Do I know the time it takes to go up vertically? Yes, I just figured that out. So I have all the information and I'm going to be able to figure out, this says delta x, but remember that it can be substituted, delta y can be substituted for that, right? Since we're talking about vertically. So this is going to mean that the vertical displacement is equal to the initial velocity vertically plus the final velocity vertically divided by 2 times the time. And I'm going to substitute those values in, the initial velocity vertically. Let's go back up, make sure we get that right. That's 19.2 meters per second. Final velocity is 0 vertically divided by 2 times 1.96 seconds. Go ahead and do that in your calculators, and you should get that the vertical height, the max height it's reached, is approximately 18.8 meters. Okay, and I don't really have a spot in there to write that into the table, and that's okay, because it's just, we can write that down here. Awesome, we're 3/4 of the way there. Again, reminder, try and do these problems or parts of the problems as much as you can individually. So if you haven't been pausing the video, maybe pause it for this last one. This last one, we're looking for the range, and I just want to be clear here. The range is this term that has specific meaning when we're doing these problems. And it's really just the horizontal displacement from where the object started to where it lands. So in other words, what I'm talking about is I'm talking about this distance here. Remember, we talked about the trajectory that the rocket would take. It would look something like this. I'm really exaggerating this, or it's just not to scale, I should say. So the range is going to be this horizontal distance, this delta x that I'm drawing in here. Okay. So how are we going to figure that out? Well, this is where we have to remember something that we talked about in class, which is one of those things about angled projectile motion. When it is in the absence of air resistance, we said that there's a relationship between the range time and the max height time. And it was 2 times the max height time gives you the range time. And again, I don't know that this is really something you have to memorize in that way. I would actually suggest you think about it in terms of the symmetry that we talked about here. This is a symmetrical relationship because it's a parabola is the shape. So there's, half of the problem can be replicated on the other half, so to speak. Okay, so I would say then T range equals 2 times, what was the max height time? It was 1.96 seconds. So that gives you 3.92 seconds. Awesome. Now, since I know it's 3.92 seconds, so I'm going to call this range is 3.92 seconds, and that's why I'm differentiating it from max height. Okay, so I know time, I know acceleration, I know final velocity, initial velocity. And again, I like this equation down here. I think it's helpful in a lot of cases when you can use it. Since I know initial velocity, and it's the same as the final velocity horizontally, and I now know the time to travel that entire range, I can just plug that in to get that number. So delta x equals vix plus vfx, initial velocity in the x direction, final velocity in the x direction, divided by 2 times the t range. If I want to be super explicit, I could just say delta x range just to make sure people understand. Okay, so the range is going to equal, now here we have to remember what's the initial velocity horizontally, right? And a lot of times I'll see students put in something like 9.19.2. You have to remember, you have to come back to this number. So that's 14.4 meters per second plus 14.4 meters per second divided by 2 times 3.92 seconds. When I do that in my calculator, I get an answer that is approximately 56.4 meters. So that means the horizontal distance that the rocket traveled from when it was launched to where it landed is approximately a little over 50 meters. Okay, so again, the goal here was to help you understand how to problem solve these types of problems. You will definitely need to do this in future assignments, and I hope this was helpful. Thank you very much. Take care.